Okay, so let's talk about how the data is processed to prepare it for machine learning, which turns out to be quite a chore and disturbingly involving a lot of human estimates and guesses. So you look at the picture, you get your data, then you explore and visualize the data to understand its structure, and you prepare the data, which often involves modifying or discarding part of it, which is, as a research scientist, that troubles me, but that's the way it is. Then you train your model and have a solution. So uh, there's a lot of open repositories of data. We'll use quite a few of them in these hands-on projects, and they're really quite useful that you don't have to hunt around for data. And so first you look at the big picture, and so in this case, what we're going to do is we got a bunch of data from, I think, some government agency that divided the state of California into a bunch of zones, sort of like counties, but smaller. And it calculated the number of people that live in that zone and various other parameters, and then the median house price in that zone. And what we would like to do is to predict the housing price from other metrics. So then they can decide where to invest in housing stocks or something. So here's your pipeline. You have upstream data that gives you district data. Then I'm going to predict district pricing, and they're going to use that to decide what to invest. That's the idea. So we've got supervised learning because the data does come complete with labels. Each zone does have the price from the government in there. And we can then do regression. Regression is where you fit a model to some data that depends on inputs, and you use it to predict results based on other inputs. And we're going to use batch learning. We're going to train it on one batch of data, and that's it. We're not going to add any more data later. So here's types of regression. Multiple regression. We'll use multiple input parameters to predict an output parameter, and that's what we're going to do here. The alternative is like what we were doing before, where you have a nice curve on graph paper, univariate regression, where all you have is X and Y, and you have the one parameter X that's used to predict the output Y. You could also have something where you predict multiple outputs, but we're not doing that. So you need a performance measure. And as I mentioned before, the standard one for centuries has been root mean square error. You take the actual observed value of the Y parameter, in this case, it would be the housing price, and you compare it to the predicted housing price, and you take the square of the difference and add them up. So large differences are considered more important than small differences, and this is what Euclid did. It's called L2 because it raises the error to the power 2. That's one norm you can use as a measure of the quality of your model. This is an error, so the smaller this number is, the better your model is fitting the data. And there's another one available too, L1, where you just take the absolute value of the difference. And this way, large differences are not considered more important than small differences. And that's the first power. And sometimes this is better. It just depends on what sort of data you have and what sort of noise. And often, as we're going to see, you combine the two. Okay, so we're assuming the price is a numerical value. Now, if the next stage just uses categories, and we are going to see cases like this, like cheap, medium, or expensive, then you're doing a classification task instead of regression. Regression is where you're trying to predict a numerical value. If you have just categories, then that's classification, sorting things into categories, which is somewhat different. So you have to get the data. In this case, we just load it from GitHub. There's a GitHub depository of this data, which I think came ultimately from the government. And then you can examine the rows, and we're going to do this hands-on part. But you see the data has a lot of fields. It has several numerical fields, like the total number of bedrooms and the median income and the median house value. And then it has a category field called ocean proximity that just has a few alphabetical values, not a number. That's not numeric. And so if you count the statistics, you'll see it has 5 possible values with this many instances in each value. And you can use describe to show statistics of things. See, I'm getting some funny noises. And like mean, standard deviation, and so on for numerical values. And that can help give you an idea. As we're going to see later in the projects, often scaling values is really important. In this case, it's not going to matter that much. And then you can do histograms. And I think I'll talk about them in more detail when we get to the hands-on portion, as you see how you can judge the data. But I just point out one of the many flaws here if you look at the median house value, it's got a sort of Poisson distribution and then a huge spike here. So obviously, the data is not really accurate. 500,000 is apparently the largest possible value. So this really means 500,000 or more. And that means it's not really representative of the trend. And that's a problem when your data is not really a numerical value like you think it is. So that's the game here. Median income, there's other capped values. Like I mentioned, median age and house value were capped, which is a problem. So if you want to deal with this, you have a whole spike of data at 500,000, but those are not really accurate measures. So there's two options. One is just remove them or somehow collect better labels for that data. And scaling is a big issue. If you want to deal with attributes that have a different scale, especially if they're in the output values, then one parameter might be far more important than the other, and you have to make sure that's what you really want. So you often have to transform things. And we talked about this before. You take 20% of the data to make a test set. Even this is going to turn out to be a little difficult because if you just take a random 20%, then it might not be representative of the mean. If you have certain parameters that are really important, then you do stratified sampling where you make sure you correctly sample each of the important categories. So here's random sampling. If you consider something that depends on sex, say, measure something about human life that's different for men than women, 51% of the population is women. So if you make a random sample, it might contain only 48% women or 54% women, and then your random sample would really not be representative of the population. So instead, you do stratified sampling, where you break it into categories and make sure you have the right percentage of each of those categories so your sample is not biased. That's what's recommended there. And so you explore and visualize the data, and we'll do this in the hands-on part, but you have various ways to display the data. You can show dots, but then if there's many dots piling on top of each other, you can't tell them apart. So if you make them transparent, you can see more the areas that are dense, and you can add price with color and see what anybody could tell you that the coastal houses are worth a lot more than the inland houses. And then you can do correlations with various parameters. And remember, correlation coefficients measure how predictive something is. So in this case, of course, we're trying to predict house value. So the house value is 100% correlated with it. If you look down here, income is very strongly correlated, 68%, which means this is a really strong predictor. Total rooms has some predictive value. These things here have almost no predictive value. And latitude has some predictive value, although in a negative sense, the higher latitude leads to lower prices. So that's one thing when you have measures. Now, in real data, these are not independent measures. And therefore, some strange things happen. You can see here the relationship. Here's median income to median house value, and that is the strongest relation, a very strong slope. Here's like no significant correlation at all. And so you can look at the scatter matrix to get an idea of what's more important. This is the strongest correlation. But if you take a good look at the data, you can see flaws. Like there's a lump, 350,000, there's a group of data there, and 450,000. And at 500,000, all those have an unusual lump of data suggesting that there's some data that was just rounded off inappropriately here. And you might want to exclude those from your data set since they don't represent the real trend of the underlying phenomenon you're measuring. They represent some kind of error in your measurement system. All right, and that's correlation. By the way, that's an important thing. Correlation assumes a line, so even things that are actually related to each other like this will appear with zero correlation. So that's an issue. Correlation coefficient is not a perfect measure to see if something matters. It just detects if it matters in a very simple way. And the other thing that is not obvious at all is that sometimes there are better parameters you can construct from the existing parameters. Since you have all these things like bedrooms and population and people per house, you can combine them. So I can get rooms per house by taking total rooms over total number of houses, bedrooms over total rooms to bedrooms ratio, and people per house. And these combined attributes may be more predictive than the original data. Because remember, there's nothing really very independent about the original data. And it turns out that that's true. So when you're done, you adjust things. And if you have some data that's missing a value, you're going to have to do something, eliminate the districts or the attribute, or set them to some kind of value called imputation. Just guess at some value for the missing data. And if you have something like this that is not numerical, then you're going to have to just encode it. And generally, the best way is one-hot vectors, where you just give it 5 columns and you put a 1 in one value for each one. That is the best way to represent that every attribute is in just one category. If you were, for example, to replace it with numbers like 1 to 5, that would somehow suggest that category 5 is more important than category 1, or category 1 plus category 4 would equal category 5. And you don't want to imply any of that, which is not true. This is what does not have false mathematical implications when encoding the model. And so then you want to scale things. Normally you scale things so everything goes from 0 to 1. That's a common thing you do to standardize things. Sometimes you try to even make it so it centers at 0 and goes from -1 to 1. So one parameter doesn't have a wildly different scale than another. And we're going to see how this messes up quite a few models when we get probably tomorrow to things like k-means algorithms. And then there's issues with a heavy tail that aren't really close to a normalization. This looks like a Poisson distribution. That's more a Gaussian distribution. So you could choose to scale the axis to try to make things more even. Because remember, our measure of error is likely to consider a downward error is equal to an upward error. And a skewed distribution like this might cause our model to be less than optimum. And so then you select a model and train it. There's a variety of models. You get pretty bad predictions from the simple one. Turns out a decision tree is much more powerful here. Decision trees are just a series of if statements. They don't make any assumption about things being linear or smooth, and therefore they can handle data that greatly violates that concept of being nonlinear, of being linear. And you can, instead of using 80% training and 20% testing, you can split it into 10 subsets called folds, and then train it 10 times on 9 folds and test it with the remaining fold. This is another way to evaluate the quality of your model. And random forests, we've talked about. These make decision trees and then make many of them, like 500, and average them so that you hopefully will cancel out the noise. And then you can do fine tuning on your models. This is going to add hyperparameters, which we talked about before, which are scaling factors that smooth out the model at the expense of being a less perfect match to the training set, but hopefully being a better match to the test set, better generalization. And you, in order to tune your hyperparameters, which are how much smoothing you put in, you typically just try a lot of hyperparameter values and then evaluate the model to see how accurate it is. You can use ensemble methods where you combine several different types of models and average them, hoping that the different types of models will have different errors. And once you're done, you deploy your model, perhaps as a web app, and then use it, as I was saying in this example, to predict your investments in real estate in California. And then you monitor it. This was in the security part I talked about in the first lecture. You need to measure the performance of your model and see how well it works and notice if it's getting worse. In particular, we're going to see the data here is from the 90s, so these housing prices are all ridiculously too low. Housing prices in California change really fast. So this model, in fact, would greatly degrade after just a few years, I would think, as the housing prices would turn out to be very different than what they were in the 90s. All right. And you have some kind of measure of success required. And so you might have to keep on retraining your model or doing some kind of improvement, and you got to keep backups of all your models. You may have to go back. So it can be quite a chore to maintain your machine learning model and keep it valuable. So I'm going to stop this lecture bit and we'll go into the hands-on. I'll make a separate video because